Okay, inner chapter C, molecular orbital theory and chemical reactions. All right. What we've covered so far is we've learned how to use curved arrows to show the movement of valence electrons. Okay. We haven't mastered it. I can't say that we've mastered that technique, but we've learned what it's for and some of the things we can use. We're moving those electrons from electron-rich to electron-poor sites. That's typical of any reaction. It's going from nucleophile to electrophile. And in order to do that, we have to know how to draw Lewis structures. So you should have mastered drawing Lewis structures and the shortcuts that are available. For instance, if we have an oxygen bound to something and then bound to something else, how many unpaired electrons will it have? It'll have two here, two there. That's always the case. If it's only bound on one side, then it'll have those and it'll have a negative charge. Right? And you can calculate the formal charge and prove to yourself that it's negative. Carbons always have 4 bonds. It may be 4 single bonds, it may be a double and 2 singles, it may be. So anytime you see a carbon, if it's only got 1 bond to it and we haven't assigned a charge, then it's got 3 other bonds that are not shown. And those are always hydrogens. So if we drew a molecule like that, right, this one would have 2 hydrogens. This one would have 3 hydrogens. So with that, okay. If we create a carbon with only 3 bonds, then it's going to have a positive charge, and that's your carbocation. Okay. Nitrogens. When nitrogen is bound to something, if it's bound to 3 things, which is normal for it, it's always going to have 1 lone pair. That if we add something else to it, right? If we use those that lone pair to make another bond, make it a quaternary, then it's going to have a positive charge because it had 2 electrons that are assigned to that nitrogen first. Now only 1 of them is. So that means it's positive. Okay. Oxygens, nitrogens, all the halogens can only have 1 bond. Right? There's your halogen. And they're always going to have 3 lone pairs. Let's see. And my periodic table's down here, so I'm going to scratch my head. Oh, sulfurs. Sulfurs are going to be like oxygens, right? They're in the same group. So if sulfur's bound to something, right, like that, it's going to have 2 lone pairs. Okay. Now, where does that fit in with molecular orbitals? Well, we're not going to treat molecular orbitals in a rigorous fashion like we would if this were sending you to a chemistry degree. We're going to use a modification to molecular orbitals called the frontier molecular orbital theory. And this allows us to account for the flow of electrons in elementary steps. It also helps us understand stereochemistry, because once we start reacting, say, a nucleophile with an electrophile, where is it going to attack? Right. Well, up to now, we just said it's going to attack the nucleophile is looking for electron deficient, electron excess. No, electron deficient. Nucleophile usually has a lone pair that it's going to donate. So it's going to go over here and look for an electrophile, which is looking for electrons. Well, sometimes, say this carbon is like this, this, and this. Sometimes it'll attack from here. Sometimes it'll attack from there. you know, front side or back side. And there are various factors that enter in, and one of the factors is interaction of molecular orbitals. You have to have substantial overlap of molecular orbitals in order to have a stabilized intermediate activated complex. You know, when we draw the energy diagram for the progress of a reaction, and we have energy here, and we say we're starting, let's start here with our reactants. We go through an activated complex or an intermediate, right? There's another name for it. Activated complex, or escapes me. And then we go to products. So that would be an exergonic, right? It would give up energy. Well, the height of this one right here determines how much energy is required to get it to that point. If you have substantial overlap, and I'm kind of stealing my own thunder because there are slides to this effect in a minute. If you get those molecular orbitals to overlap significantly, then you can reduce the amount of energy required. Now, in general chemistry, that would signify a catalyst. But in organic chemistry, we were saying that this activated complex is lower energy because it's more stabilized by that overlap. If you don't get significant overlap of the molecular orbitals, it takes more energy to get to that complex. Okay, that's what I'm saying. I should be using this rag. I'll do a better job. Yeah. Much better. Okay. So that's where we're headed. So here's another use of the term stabilization. When we think of stabilized, we always mean lower energy. If you can lower the energy of the complex, it's more stable and it's easier to get to there and over the hump and toward products. That's what that graph is showing, where if you don't have stabilization, transition state. If you don't have stabilization of the transition state, then it takes more energy. That's the red curve. If you have significant stabilization, then the energy barrier is lower. All right. So in order to get there, we're going to use this frontier molecular orbital model. And that's where we introduce the concept of HOMOs and LUMOs. The highest occupied molecular orbital is the molecular orbital on an energy diagram. Say you have a HOMO here, and it's got an electron pair in it. And this is our nucleophile that's going to be looking for an electrophile. The electrophile should have its lowest unoccupied molecular orbital. Okay, and when they interact, then you form a complex here that's at a lower energy. There's a better picture of that coming up. But what we want for the best possible outcome for predicting which one of the elementary steps is going to be useful, or even if it's allowed, is it allowed or prohibited? If it's allowed, then you've got significant overlap of those two orbitals. Allowed or forbidden, that's the terminology that's used. Okay, so here, excuse me, our example on the left says the interactions that we're interested in is the highest occupied molecular orbital and the lowest unoccupied molecular orbital on the other reactant. And there they've drawn the diagram. The transition state is actually, the lower we can get that transition state, the better. The lower energy means that we have a smaller hump to get over in that energy diagram. Okay.
I'm like, can you say that one more time?
Yeah. So the corresponding difference here, if we're starting off with that much energy, then this difference here, this change in energy, will give us this lower value here. This transition state is at lower energy. As we lower this transition, and this is only temporary, right? When these things overlap, this is temporary, and we'll get a different set of molecular orbitals for the products. This is intermediate. This is on the way to the products from the reactants. These are the reactants, and this is an intermediate step right in here. The lower we can get that delta E right here, the smaller the hump and the more stable the transition state. Stable transition states, relatively speaking, contribute to picking the correct elementary step in a reaction. And now, going back to general chemistry, what are we talking about here? If we're in this region right here, right, in this region right here, that's kinetics. If we talk about only this region and this region, devoid of that, that's equilibrium. Okay, we're talking about kinetics. Let's see. What's today? Tuesday? Wednesday. Thursday, we have an exam on this stuff, don't we?
Yeah.
On the equilibrium.
Unfortunately.
So don't get this confused with equilibrium. This is kinetics. All right. We have already covered kinetics, so you should be well versed in that. Okay. So the HOMO is always coming from the electron rich or the nucleophile side. So let's see. Names that'll be used in these terms. Electron rich. We're also talking about nucleophile. That just means nucleus loving or positive charge loving. Or Lewis base. Remember, Lewis bases donate electron pairs. We haven't got there yet. That's chapter 14 and 15. And then, of course, electron poor would be electrophiles, electron loving, and Lewis acid. That's electron pair acceptors. Okay. Well, to make in fact, the concept of Lewis acid and Lewis base was developed for organic chemistry because you don't always have the luxury of using the Bronsted-Lowry definition, which is proton donors, proton acceptors, because there's not always a proton there. Now, if we're talking about the proton transfer reaction, yeah, you can talk about it in terms of Bronsted-Lowry's. But Lewis base and Lewis acid covers everything. It's all inclusive. All right. Now, what we need to make the frontier molecular orbital theory work for us is to recognize some characteristics that simplify things. The first thing is that coordination and heterolysis are opposites of one another. Remember, coordination Remember, in general chemistry, we talked about a covalent bonds. Very often what you have is, right, these two reactants, and they form a bond, right? One electron from one electron from the other. But if both electrons come from one side, that's a coordinate covalent bond. And that's what we've seen in that coordination step, where you have the nucleophile attacking with its electron pair, and it forms a bond with that pair. Right? That's a coordination. Now, heterolysis is just the opposite, right? If you have this bond, and then both of those electrons, say now, both of those electrons are going to go here. Now we have this one, and that one's deficient. So this is probably negative, and this is probably positive. It doesn't have to be, but I'm just speculating. That's a heterolysis. Hetero means other, right? There are processes that are homolytic. One electron goes one way and one goes the other way, in which case you form free radicals. Right? So they're not as common. What I'm trying to say is that coordination and heterolysis are opposites of one another. So if coordination is permitted with a certain with the coordination step is permitted, the heterolysis, the reverse of that one, is also permitted. Nucleophilic addition and nucleophile elimination are opposites of one another. And electrophilic addition and electrophile elimination are opposites of one another. So that says if we can say that coordination is permitted in a certain case, nucleophilic addition is permitted in a certain case, electrophilic addition in another case, then their opposites are also permitted for that reaction. The forward direction, if the forward's permitted, the reverse is permitted. And they have to go through the same transition states. It's just that if you have a situation like this, what's the activation energy for this direction? It's from here to here. It's a lot bigger. So just because it's permitted doesn't mean it's going to happen. Right? Because it takes a whole lot more energy to go backwards in this one. Or if we had an endergonic reaction, we'd be down here with reactants and over here with products. So the forward would be difficult, but the reverse would be probably fairly easy. All right. Let's see. This principle of microscopic reversibility, I mentioned one of its characteristics, and that is it follows the same path in the energy diagram if it's reversible. Microscopic reversibility just means that on the local level, like on the molecular level, the reaction is reversible. And I mentioned also that we're talking about kinetics here. So what would it look like for, say, the first elementary step we learned was proton transfer. All right, so we get this, use this, I'll erase better. Let's see. Yeah. So the HOMO is always going to be the nucleophile. It's got the extra electrons. And the LUMO is going to be the electrophile. So for our proton transfer, a good example would be this very, very strong Lewis base, right? The hydroxyl ion. And it's going to attack some acid. Actually, it's going to attack this electrophile. So we know this bond is extremely polar. That means this one is slightly positive, and that one has a full negative charge. So what we're going to get is two of these electrons are going to attack that electron deficient site, that hydrogen. And when it does, tries to form a bond here. Now this one has to break, right? It cannot remain because hydrogen can't have a bond on either side. It can only have one bond. So when we form this bond, that one has to break. There's no way around it. This one has the LUMO on that hydrogen, and this one has the HOMO on that oxygen. That would make this a Lewis base, and this is a Lewis acid. Now, the representation of the molecular orbitals in this diagram tells us that if this hydroxyl attacks that hydrogen from this side, it's going to have substantial overlap of the LUMO and the HOMO. So that means it's permitted. This reaction is allowed. If it, I think the next diagram, yeah, if it approaches from here in space, then there's not going to be substantial overlap. So that approach is not allowed. That's forbidden. So only when it approaches from here will the reaction proceed. It's allowed. And that goes back to my general chemistry discussion of what do you need for a reaction to proceed? Well, you have to have enough, you have to have the activation energy, right? This is the collision model for a reaction. So when the two reactants come in at each other, they have to have enough energy, kinetic energy, to supply the activation energy for the reaction, right? They've got to get up the top of that transition state, right? They also have to have the proper orientation. In order for the transition state to form, they've got to approach each other from the right side. If the bond is supposed to form on this side of this molecule and this side of that molecule, if they come in like that, nothing happens. Doesn't matter how much energy they got. So they have to approach from this side with that energy. And that's what we're saying here. This overlap can occur if the base is approaching from the wrong side. So not every encounter of the Lewis base with the Lewis acid will result in a reaction. Only when it approaches from the correct side. And that concept of a three-dimensional attack, which direction does it come from, is one that will persist in organic chemistry. It will also lead to certain types of stereochemistry that are allowed and certain that are not allowed, forbidden. So that's also where we're headed. Well, where we're headed. We might get a little bit of it in chapter 8 when we start talking about we're combining elementary steps into a complete reaction. That's where we're going to end for you guys. Okay, so that was, let's see, that was proton transfer. Okay, now we're going to look at SN2. Remember what SN2 stands for? I look at it, I go from the back to the front. 2 means bimolecular. That is, there are 2 reactants that have to approach one another, right? The nucleophile and electrophile. And this is the nucleophilic substitution. So this happens on a carbon. So if you have a group here and you have a nucleophile attacking here, this nucleophile is going to form a bond there, and that one's going to break. So that the nucleophilic substitution always happens relative to one carbon. This is the leaving group. I should put an L there. That would be more appropriate. This is the leaving group. Now, the best leaving groups are the ones that are the most stable once they've left. They're conjugate bases of strong acids. Okay. Like chloride would be a good one. Bromide would be an excellent leaving group. Large charged species with the ability to resonate, they're also good leaving groups because of their stability. So when this bond forms on this side, that one has to leave. Well, what happened? Well, this one has the HOMO, occupied molecular orbital, and this one has the LUMO. Their interaction is what precipitates this reaction. Let's see. Well, okay, we're using the hydroxyl again as a strong Lewis base. Okay, that's the example. Let's use it. Let's use their example. All right, so we've got this methyl chloride. And since this is a very strong electronegativity, it's causing that bond to be polar, and that is translated to this carbon. So this carbon is slightly positive. And of course, that Lewis base is coming in with its HOMO overlapping with this LUMO, and these electron pair are attacking that electron deficient carbon and form a bond with it. Right? So in order to complete the reaction, we can't exceed the octet with carbon. That's forbidden. So if we form another bond here with that carbon, that gives it 1, 2, 3, 4, 5, or 10 electrons. Can't happen. So that's why this one breaks. And that gives us, let's see, there. That gives us this. The chloride ion. That's the leaving group. All right, so the action that precipitated this was the overlap of this occupied molecular orbital with this highest unoccupied molecular orbital. All right. As far as it goes. And there again, the direction of approach matters. In this case, this highest unoccupied molecular orbital from the hydroxyl overlaps an unoccupied, overlaps a lowest unoccupied molecular orbital for the carbon. Now this carbon is sp3 hybridized, right? So if it's sp3 hybridized, all the orbitals are occupied. All the hybrid orbitals are occupied. So it must be overlapping a higher unoccupied molecular orbital than this right here. That's the only thing that makes sense. The way it's presented here, I think we're seeing that this carbon and the chloride there's one lobe of that orbital that's overlapping here to make the bond. And then the other lobe over here is being used as the LUMO. Now, I think this is taking liberties here with molecular orbital theory in order to emphasize this point, HOMO and LUMO overlap. All right, so let's see, that's a new one. All right, so the direction of approach also matters here. What's the next one? Well, what we have? Bond formation and bond breaking. So in this case, in order to a coordination step. In this case, we have this, let's see, what would that be? Let's see, that's a propyl. That's a 2-methylpropane, right? Carbocation. 2-methylpropane carbocation. So when we have this carbon in here with a positive charge, and we've only got 3 bonds to it, that means it's sp2 hybridized, and we've had an unoccupied p orbital. That's the LUMO. The LUMO, in this case, is an unoccupied p orbital. Right? There are no electrons in it. So that makes it deficient, of course. And when we approach it with this bromine, or bromide ion, actually, then the attack here, we form a bond with using those 2 electrons. We form a bond there. So now we have the bromine, carbon, and we have these, let's see, we have these methyl groups. I'm going to abbreviate ME. Now, just as a side, that carbon is now sp3 hybridized. So this is the coordinations elementary step. Let's see. Now the heterolysis. Okay, we're going to talk about the overlap first. In this case, since that carbon is sp2 hybridized, what type of geometry does it have according to VSEPR? sp2.
What's the question again?
What type of geometry does that central atom have? If it's sp2 hybridized, right, it's got that.
120.
Yeah.
Is that what you mean?
Trigonal planar.
Yeah.
Yes, trigonal planar. What that means is that this bromine can attack from one side or the other. It doesn't matter. And that's what we're trying to show here. The overlap, this overlap can occur here, or it can occur here on the other side. What that does is it leads to the potential for a different stereochemistry. Right? This one's not going to matter, right? Because you've got 3 methyl groups. That's not a chiral carbon, right? Because you've got these 3 are all the same, and that one's different. In other words, when you have a chiral carbon, you need what? You need 4 different groups around that carbon in order to form a stereochemical site, right? So if we had different groups around here, if like a methyl here and say a benzyl here, well, that's too big. Let's make it methyl, ethyl, and propyl. If you had those 3 different ones, then the stereochemistry would be different. It would be R one way and S the other way. Okay? Or make one of them hydrogen. Yeah, make one of them hydrogen. Hydrogen, methyl, and ethyl. And then the bromine comes in from one side, it makes one stereoisomer, comes in from the other side, makes a different stereoisomer. But both directions are allowed. Okay, heterolysis. Let's see, this was coordination. Trying to keep track of the ones we covered so far. That was coordination. Now the opposite, which is heterolysis. Is presented here with let's see, I'm trying to get my names right. Cyclohexyl iodide. No, it'd be iodocyclohexane. There you go. Iodocyclohexane. Iodine is an excellent leaving group, right? Because it's the conjugate base of a very strong acid. Those are very stable conjugate bases. The iodides, the bromides, chlorides. So heterolysis here is very likely. So what happens? Well, both the electrons in that bond transfer to the iodide, and that leaves you with a carbocation. Now, this is allowed simply because the coordination step that would have formed the molecule going the other direction is also allowed. That's what we're saying. If this is permitted in one certain situation, that's permitted in the opposite direction. All right, nucleophilic addition. What's the difference between nucleophilic addition and bimolecular nucleophilic substitution? In nucleophilic addition, the nucleophile attacks the electrophile and forms a bond. And in so doing, it does not eliminate. All right, let's go back, because I know what you're thinking. Right, why isn't this one a nucleophilic addition? Well, in most nucleophilic additions, the carbon is connected in some way, a double bond to something else. It has pi electrons. So the nucleophilic addition in this case is being added to this, let's see, this is scratch my head, trying to name that electrophile. That's ethyl, there's another name for it. Actually, we're going to cover that in the D section, so I'm going to leave it alone for now. Anyway, that carbon is deficient because it has oxygen attached to the carbon and it has chlorine attached to the carbon, which are strong withdrawing groups. They pull electron density away. So that carbon is extremely deficient in electrons. So the nucleophile attacks the electrophile at that carbon. That's one thing that always puzzled me. You know, when these organic chemists like Dr. Van Branken start talking about, you know, this nucleophile comes in and attacks here. So how do you know it attacks there? Well, apparently, you need to know where the deficient site is. Right? In this case, we've had it identified that carbon is slightly positive. That's why it attacks the carbon and it doesn't attack some other part of the molecule. So when it does that, we're seeing the hydroxyls, highest occupied molecular orbitals attacking the LUMO for the other species at the carbon. As it turns out, and I'm not sure how they figured this out if you don't actually draw the molecular orbital structure yourself, how they know that it's a pi star molecular orbital that's on the LUMO. Your guess is as good as mine at this point. But it can attack from two different sides, right? That's pi star molecular orbital actually has two lobes. So it can attack from one direction or it can attack from the other direction. And that tells me that this can also lead to a different stereoisomer. In fact, I suspect it does. With a hydroxyl on one, a chloride on one, a double bonded oxygen on the other one, and a methyl group on the other one. Those are four different groups. So this is probably will lead to a different stereochemistry depending on which side it comes in. Okay, that was nucleophilic addition. Nucleophile elimination. Nucleophile elimination. So in a nucleophile elimination, you've only got the one molecule. And let's see. I think, okay. We're using the simplification here. The nucleophilic addition is the opposite of the nucleophile elimination. So instead of a hydroxyl attacking and forming a bond, let's see, I'm going too far that way. In this case, the chloride is the best leaving group. So it's the eliminated part. This would be the nucleophile elimination. The chloride is a nucleophile because it's electron rich, and it's being eliminated from the molecule, largely because the molecule is negatively charged on that oxygen, and the chloride is an excellent leaving group. So it's taking the negative charge with it by breaking that bond, and then the oxygen is stabilizing itself by forming a pi bond out of one of that pair. Okay. All right. Biomolecular elimination, E2. The 2 always means bimolecular. We also have SN1 and E1s. But in this case, we have bimolecular elimination. So in this case, what we're doing is actually, when this happens, let's use their example. They've got the hydroxyl here with its negative charge, and we've got the electrophile, which is this one. And this is another hydrogen up here. This one has 3 hydrogens on it, but we're separating that one just to make the point. But this one has a bromine on it. Okay. Bromide is a good leaving group. And the only thing that can explain that possibility is induction. Right, this bromine is drawing electron density away, and it's not very effective, right? Because you're 2 carbons away from that hydrogen, right? So induction is pretty weak, but apparently it's strong enough to make these hydrogens slightly positive. Well, carbon is more electronegative than hydrogen anyway, so that contributes. And then you get a bond formed there, right? So what's the consequence there if we do this and we put those there, that forms a double bond. You break this bond, we form this bond. So what do you get here? Water. H2O. And what do we get here? Well, we have to break another bond. We have to take these 2 electrons, put them on that bromine. So now we've got the bromine negative, and we've got this molecule here, and we have water over here. So we've eliminated the electrophile. Bimolecular elimination. Yeah. So in the process, we formed how many bonds? We formed a bond here and we formed a bond there. 2 bonds are formed. How many bonds are broken? That bond's broken and that bond's broken. So you form 2 bonds and you break 2 bonds in a bimolecular elimination. Okay, so I assume on the next, we're going to talk about, are we still talking about E2s? Yeah, we're still talking about E2s. Okay. So the whole process is initiated by this Lewis base. It overlaps its HOMO with a LUMO here. So we've got this one interacting with this one. Right? And if it approaches correctly and the overlap is made, then you start to form the bond and that you form an intermediate. Right? So sometimes we write it like this. We'd have this carbon and this hydrogen here, and then all the other stuff over there. And then we have this like that, like that, like that, like that, like this, that. So in the process, this intermediate state will have a, what in the world are you
I
doing?
just pulled that out of my book bag.
Tangerine in your, that is a tangerine, isn't it?
Yep.
Okay. I guess depending on how long it's been in there, it could be an orange.
It's been in there a minute. Seems like last week.
Oh, okay.
Anyway.
So you need some Lysol spray maybe. So the intermediate that forms with this overlap, we often write it here with these dashed lines to form partial bond breaking and partial bond forming. That's the intermediate. And then let's see, once we've got that overlap, yeah, we have the overlap here of these two. Oh, okay. So, since we have a double bond formed in this process, we can and before this bond is formed, before the double bond is formed, this bromine can be up here or down here, right? Because it could rotate around that sigma bond in the process. So, and it's constantly rotating. I mean, if we look at our Newman projection, we could see it like this, and it could rotate around here, it could rotate around there. So this could be, it doesn't have to be down here, it could be up there. And if this is the process that happens, then we're saying it's an anti-conformation. So this side, the attack is occurring on the opposite side of the molecule to the bromine, the leaving group. That's an anti-conformation. If the bromine is up here, right, and we do that thing, then that's a syn conformation. Either one can happen. And since bromine is only, since we only have bromine here and it's leaving, and we have nothing but hydrogens left, the stereochemistry doesn't matter. If we had something else here besides the hydrogens, then the anti-conformation would give you a different isomer than the syn conformation. And you would either have a Z or an E. Right? It'd be on the same side or the opposite side. Okay. That was the second step. Let's see. Yeah, the second part. Now, how about electrophilic addition and eliminations? This was an E2 reaction. Bimolecular electrophile elimination. This is addition, electrophilic addition. Elimination was first, right?
No, addition.
Addition.
Yeah.
Get them in order. And then the opposite of that is electrophilic elimination. Okay, this one's petering out too. I'm gonna have to dig into my bag. All right. So the nucleophile attacks the electrophile. And in this case, we have there. Now notice there are no lone pairs here, but we do have pi bond electrons which are not as tightly bound as the sigma bonds. Right, so the pi bond electrons are available if the electrophile is strong enough. Right, and in this case, it is. Right, this is extremely positive. Right? The polarity of the bond is that way. So what happens is these pi bonds, this bond breaks, the pi bond breaks and delivers its electrons to that hydrogen. And there again, so that we don't exceed the duet, this bond also breaks. And that gives us this excellent leaving group plus that molecule. Oh, well, if both of these electrons leave, then we're going to end up with a positive on one of these, either this one or that one. I don't think it matters because all you have to do is flip it around and it looks the same. Okay. Now, what they're showing you there is that hydrogen. So we formed a bond with the hydrogen here, that extra hydrogen. But there was already a hydrogen there. So they're not showing you the other hydrogen, which is back there somewhere. That means 1, 2, 3. This one only has one hydrogen attached to it. It's sp2 hybridized. Okay. So what that looks like is in three-dimensional space, this molecule would approach like that with its pi bond. In physical space, that HOMO would have to, from here, that would be a pi molecular orbital, would have to provide the electron pair to make that bond. Oh, they put it in red down here. So maybe I do know something. Not a lot, just something. As long as we have that net overlap, then you can say that the process is allowed. Now we're saying that well, now this one makes sense, right? That hydrogen is bonded through a sigma orbital, right? Sigma from its 1s. That means that an unoccupied sigma star, hydrogens are easy to do because we've only got two possibilities, right? It's a sigma from the 1s or a sigma star from the 1s. And since this one's occupied, in this process here, it's occupied in that bond, then the only attack they can make, the LUMO, has to be this one. Right. That's easy. Some of the others are not as obvious, but that one is. That's if it's obvious to me, it's got to be glaring. Okay, electrophile elimination. So in this case, we still have a nucleophile attacking an electrophile, but in the process, it's the opposite of the addition. Right? Instead of adding to, we are eliminating. We're removing the hydrogen to form a hydronium, right? Because we've got water molecules that have the oxygen has extra lone pair, and it attacks the hydrogen. Now, we're starting from this one, not that one. We're starting from this one. So that means if this is positively charged, it makes you wonder, why didn't it attack down here? Now, why does it attack up here and not down there? If this is positive, it's probably drawing electron density away from this part of the molecule. It's trying to absorb the negative charges. So we're moving the negatives this way, and I guess that's what makes this one positive. Right? Instead of attacking, I think, this is just my thinking. The possibilities for this one, right? If we're talking about electrophilic elimination, that's a possibility. But the other possibility is it could attack that carbon, right? Because it's positively charged. So I think later on we're going to see competition. I don't think we're going to see competition discussions in chapter 8. I think it's coming in the second semester. The competition between these elementary steps, see which one is most likely. But I think this is a possibility that's obvious to me. Right? If that's a positive charge, why didn't it attack the positive? Well, it's because we're not talking about that one now. We're talking about this one. That's the only thing that makes sense. But when it does that, of course, it produces this molecule here by eliminating the hydrogen. And the only reason that we can say it's allowed is that it's the opposite of this one, which we've already determined is allowed. All right. So what's next?
Carbocation. or-
Carbocation rearrangements. Okay.
Carbocation, sorry.
Yeah, I guess in maybe in the islands that would be carbocation.
Yeah,
So you can have two possibilities for carbocation rearrangement. One is the hydride shift and the other is the methyl shift. So I think we're just going to talk about the hydride shift because the methyl shift should work the same way. And so this would be 1,2 hydride shift. And we should be able to do a 1,2 methyl shift also with this same discussion. Now, when we look at it from the interaction of homos and lumos, then I think in the when I did the video and talked about these things, I mentioned the possibility that perhaps that hydrogen transferred to something else and then came back. But according to this discussion, it can actually shift on the molecule. It doesn't need to, the hydrogen doesn't need to leave and then come back. I think that's a possibility. But when we're talking about this rearrangement, it's actually an overlap of within the molecule of a HOMO from the hydrogen and the LUMO from the carbocation side. And you shift that hydrogen over. Now, when you break that bond, right, we break, I wish my cursor were bigger. When we break that bond, that makes the carbon that the hydrogen left, that makes that positively charged. And now those 2 electrons that were holding the hydrogen are donated to the carbon and form a bond there. Now, which one is more stable? Right, which side should be more stable? Let's look at that while we're here. Let's see, it goes. It's like that, right?
Yeah.
We're starting off with this one, and we're saying that's a hydrogen. This is a methyl group. Let's see, there's another one up here. There's another methyl group. Okay. So this carbocation is on a secondary carbon, right? When we do the transfer, like when we do this, and we form put the hydrogen here, now What carbon is that carbocation on? 1, 2, 3. It's on a tertiary carbon. This one is more stable. So this shift should prefer that side rather than shifting back. It shifts this way and largely stays this way. All right. So what this is leading to is if a certain reaction, when we start combining elementary reactions, if this is the product of a former step, an elementary step, then it's not going to stay there. We are going to have, more than likely, we are going to have a hydride shift and leave us with this carbocation as a product because it's more stable. Oh, that's all for C.